concrete design is a little bit different than the first course, structural analysis or engineering mechanics. This course is a long story. Long story. What you mean by long story? I mean each part is built based on the previous part. I know we have different topics in this course, but each topic is built on the previous one. So, for example, until this moment, because you're still asking for something, you can't figure it out. Many students ask me about what is the value of N. N is E steel divide E concrete. E steel, it's not given. You have to remember it. 29 million PSI. E concrete is not given. Okay. But probably F prime C is given. So I can figure out E concrete equal 75,000 square root of F prime C. Okay, F prime C is not given in the problem. Okay, go ahead and assume it. How can I assume F prime C? The typical values for F prime C in your design from 3,000 PSI to 5,000 PSI. Something in between, 3,000, 3,500, 4,000, 4,500, 5,000, that's fine. You know, so I'm telling you along the story. So you need to remember all of these parts when you are going through this course. Okay, so please, I put at the beginning of each homework, assume any missing data. So you can assume what you want. As I told Burak, in this course, you will assume something from nothing. You don't have an existing building. You will create this building. So we will assume, and based on your assumption, we will design. And also be careful, your assumption must be more realistic. So don't assume F prime C equal 10. What is the meaning of 10? Don't assume F prime C equal 1 million. No, you are kidding me. F prime C, the typical values, if you go back to our previous examples, F prime C something between 3,000 and 5,000. If you go below 3,000, you are talking about very weak concrete. If you go over 5,000, 6,000, 7,000, 8,000, 10,000, it's okay, but it's a different concrete called high strength concrete. No, the typical or the normal or the common concrete used in design, the F prime C between 3,000 and 5,000. So from F prime C, I can figure out E concrete. From E concrete and E steel, I can figure out the modular ratio, N. Okay? So all of these stuff, put them in your mind. Any question, guys? Any question? Any question? Okay, we have very interesting story this week. Just to remind you, in this week, we will learn what's going on in ACI. Everything related to concrete design is included in something called American Concrete Institute Standard, ACI 318. Probably the version right now for 2018. If you have a chance to look to this standard, that will be great. If you have a chance to buy it, it will be a great chance. If you don't, I will provide you with everything. Don't worry, okay? So everything related to concrete design is included. It's not my method. It's not my suggestion. No, it's American Concrete Institute standard. We have first case in design. What is the first case in your design? We have cross section is given. And next week, I think, I will let you know how can I assume this cross section, B and T. How can I assume this? What is the value of B? How much? How can I figure out the T? We have many things to learn about these dimensions next week. Okay, by the way, but the cross section is given. And the steel reinforcement, how much steel reinforcement is given also. Next week, next time on Friday, I will let you know how can I get the reinforcement, but step by step. We are starting from the beginning. So right now, we have a given cross section. Everything is given. Can you tell me how much bending moment this cross section can support? I'm sorry. What you mean by bending moment? I will let you know what is the end of our story. End of a story. We learned from structure analysis last semester something called bending moment diagram. We have a beam. We have external forces. We learned how to draw bending moment diagram. Do you remember? Bending moment diagram from structure analysis. Today, we have beam. Looks like this. Real beam. And this beam has steel reinforcement. Can you tell me how much bending moment this beam can support? Called phi MN, design moment. If you can figure out the design moment of this cross section with this steel reinforcement, I will do a very small comparison. What is the value of moment here? And what is the value of moment here? For this beam to be safe, for this beam to be good, for this case, this moment must equal greater than or equal this moment. This is the end of our story. This side from structure analysis, we have a beam, we have given loads. I can draw something called bending moment diagram. This moment can be called M ultimate moment from structure analysis. From concrete design, we have cross section, we have reinforcement, and I will do some calculation to figure out how much moment this beam or this cross section with this steel reinforcement can support, which called phi MN. For this beam to be safe, for this beam to be enough for this case, this moment must be greater than or equal the actual moment on the beam. Any question in this point? Any question in this point? This is the end of our story. You got it? Guys, you got it? This is a relationship between this course, concrete design, and our previous course, structure analysis. From structure analysis, we have a moment, D2 given load. in our concrete design, we have a moment can be supported by this cross section and this steel reinforcement. We need to make a comparison between this moment and this moment to be safe, this beam to be safe, this steel reinforcement to be enough. This moment from design must be equal or greater than this moment from the given or the applied load on the structure. Okay? Okay. I would like to understand. We have a cross section given. Everything is given. Dimensions and the steel reinforcement. We need to figure out how much moment this beam can support. We learned a little bit last time. Just to remind you, we have a cross section. This story is very important. This part of the story. We have a cross section. We have steel reinforcement. Between one side and the other side, we have something called neutral axis. This neutral axis at a depth equal C. On the upper part, we have compression. Looks like this. But this compression block did not reach the neutral axis, a little bit behind. This depth equal A. We have a relationship between A and C. C is the actual depth of the neutral axis from the top. A is the depth of the stress block from the top. So A equal beta 1 times C. And guys, you have to remember this part of the story. What is the value of C? Do you remember? What is the value? I'm sorry. What is the value of beta 1? Anybody remember? We have a table. Based on what is the value of F prime C, I can figure out the value of beta 1. Sometimes 0.85, 0.8, 0.75, 0.65, something like this. So you have to remember this stuff from before. This value of stress equal 0.85 F prime C. And this width of the cross section is B. So if you are looking for the equivalent to compression force in concrete, capital C, this capital C equal the volume of this stress block, 0.85 F prime C A B. And also we have tensile force, capital T, in steel reinforcement. This capital T equal area steel times F yield. For acrobium, this cross section is in acrobium. So capital C equal capital T. So 0.85 F prime C A B equal area steel F yield. Everything is given except A. So I can figure out the value of A. I can figure out the value of A. The distance between this force and this force equal D minus A divided 2. So your final moment, Mn, which called nominal moment, equal area steel F yield times D minus A divided 2. We covered all of this stuff before. That's fine. That's right. So nominal moment, which called Mn, equal area steel F yield times D minus A divided 2. And all of these stuff are summarized here. From acrobium, I can figure out the depth A. So your moment, this moment, Mn, can be called nominal moment or theoretical moment, equal area steel F yield times D minus A divided 2. But we are looking for something called design moment. Design moment we need to multiply this value by another value called phi, reduction factor, for factor of safety, more safety. You are talking about lives. You are talking about lives of people. So we need to take factor of safety. Theoretically, based on your calculation, here is the nominal moment. But we need to take a little bit of factor of safety, so we need to multiply this value by a reduction factor called phi to get that design moment. Then I will do a comparison between moment from structure analysis and our moment from design. Any question? Guys, I have something wrong with my laptop, so I will make restart. So staying, and I will be back in few minutes. I'm sorry, guys, for this interruption. Is there a reason why the compression block does not go all the way to the neutral axis? Yes. Yes. I think it has something to do with changing the slope of the distribution. Who is asking? Roberto, do you remember last week, I think, I told you we have 3 stages of concrete. The first one, uncracked. The first one, cracked. The third one, ultimate stage. Do you remember? If you go back to notes for last week, we have neutral axis for ultimate. I'm talking about this stage. The actual stress distribution of concrete, something looks like this. And I told you at that time, we have some difficulty to work with this parabola of stress distribution. So we need to make equivalent for this parabola to make it something like this. This stress block is equivalent to this shape of stress distribution. To make this block constant with a constant value 0.85 F prime C, to make it equivalent to this distribution of stress, we need to make it shorter at distance A, however, this one at distance C. So this block as an area equivalent to this parabola as an area. This is the reason, the main reason why we make it shorter a little bit. Okay? Okay. Let me continue. So, okay, I understand all of this stuff. And one of the problem in our homework, how to calculate MN, nominal moment. So can you tell me more about phi, the reduction factor? How can I multiply this moment by phi? Okay, phi, you can figure out the value of phi using this table. Sometimes phi equal 0.65, sometimes equal 0.9, sometimes something different, based on what is the strain in steel reinforcement. I'm sorry, how can I figure out the strain in steel reinforcement? Okay. The cross section, as I told you, the cross section has something called neutral axis. This neutral axis at depth C. Remember, from the first step, you are able to calculate A. That means you will be able to calculate C because A equal beta 1 times C. That's right? So A, I can get it. Beta 1 based on the table based on F prime C. So I can figure out the value of C, which is the actual depth of the neutral axis. So right now, this depth, I can figure it out. We have something called strain distribution. We have contraction in concrete, and we have elongation in steel. And if you connect between both of them, you have to pass through the neutral axis. Neutral axis means we don't have contraction, we don't have elongation, we don't have anything. Stress is equal 0. Based on ACI, strain in concrete at ultimate stage is known, 0.003. Can I tell you a good story also? Okay, let me tell you this. If you go back to our old story, we have concrete cylinders filled with concrete, waited for 28 days, and applied compression force on the concrete cylinders. And we can record the relationship between strain and stress. Do you remember this old story? We can draw this relationship to be something like this, which is called stress-strain curve for concrete. Do you remember this value? The highest value can be called F prime C. To continue this story, the corresponding strain for this stress equal epsilon concrete ultimate, which is 0.003 all the time. Something around this value. So ACI decided to take ultimate strain in concrete equal 0.003. Guys, all of this stuff you have to be familiar with. All of this stuff. Okay? So, this value of strain, I have to figure it out. It's all the time based on ACI 0.003. And see, I can get it. Can you tell me what is the value of strain in steel reinforcement? We have at this location steel reinforcement. So can you tell me what is the value of strain here? Yeah, I can do something called triangle similarity between this triangle and this triangle. I can figure out this value of distance equal D minus C. Do you remember? D, the distance between steel reinforcement and the top of the cross section. C is the distance between the top to the neutral axis. That means the remaining distance will be D minus C. If you make triangle similarity, I can figure out the value of strain in steel reinforcement. If this value smaller than yielding value of steel, we can use 0.65 for Fe. If this value greater than or equal 0.005, we will use 0.9. If this value between yielding and 0.05, we can set up this equation and figure out the value of Fe. Okay, another story. We have steel rebar under tension. So I can record the value of force and the value of elongation, so I can figure out a relationship between strain and stress. Typically, this relationship looks like something like this. For steel reinforcement, at this location, we have something called F yield, yielding. At this location, we have something called epsilon yield, yielding of stress, yielding of steel. And everybody know that E, Young's modulus of steel, equal F yield divide epsilon yield. So epsilon steel 29 million psi. F yield will be given what type of steel reinforcement you are using. Probably this value 50, 60, or 40. Only three values, something like this: 40, 50, 60 psi. So I can figure out the value of epsilon yield, yielding strain of steel reinforcement. So I can figure out the yielding strain. Why? Because I need to know what is the relationship between epsilon steel in my problem that I calculated from triangle similarity and the yielding strain to figure out the value of phi, which is the reduction factor of our design. I will go through all of this stuff by doing this example. We have cross section, and I believe you learned all of this stuff during the homework. This problem looks like one in your homework, but the only difference is fake. According to ACI 318, we are looking for design moment strength. Design means you have to multiply your nominal moment, capital MN, time phi. For the beam cross section, F prime C equal 4 KSI, F yield equal 60 KSI, and the area steel is given for number 10 bars. Okay, anybody can remind me what is the actual value of area steel? Yeah, it's 4, number 10. Okay, what is the value in inch square? What is the value? 4 times what? I need to open my tables and figure out number 10. Where is number 10? Here you go. Number 10. What is the area of this cross section of number 10? 1.27. So 4 times 1.27. So I can figure out the value of area steel equal 4 times 1.27, 5.08 inch square. I would like to remember my calculation with a story. So I have a story. We have neutral axis. I would like to solve my problem like this. In this side, we have compression. In this side, we have tension. If I would like to draw strain distribution, it will be looks like this. Linear relationship. This is strain at this location called epsilon tension in steel. Strain at this location equal epsilon concrete ultimate equal 0.003. This neutral axis has a depth equal C. We have stress distribution, but at the upper part, it's a constant stress distribution, a little bit behind the neutral axis with depth equal A. And this value equal 0.85 F prime C. We have capital C here, which is the equivalent compression force for this stress block. We have tensile force here, capital T. For acrobium, capital C equal capital T. I like to calculate, to do my work like this. I need to draw strain distribution. It will be more easy to make triangle similarity. And I would like to draw stress distribution. Please train yourself to draw all of this stuff. Capital C is 0.85 F prime C A time B equal capital T area steel time F yield. Guys, remember and be careful. Units of F prime C must be the same like F yield. If this one KSI, this one must be KSI. If this one PSI, this one will be PSI. So be careful. So I will keep both of them KSI. So 0.85 times 4, which is 4,000, times A, times B. The width of this cross section is given 12. Equal area steel, I can figure it out, 5.08 times F yield, which is given 60. One more time. 60 in KSI. Four in KSI. So be careful. Both of them must be the same. So the only unknown in this equation is A. So 5.08 times 60 divide 0.85 times 4 times 12. This A equal 7.5 inch. By the way, A equal beta 1 times C. A equals 7.5. Anybody can tell me what is the value of beta 1? Thank you, Brock. What is the value of beta 1? If I open my old, I think this one. We have a table here. Yes, this one. This table. Based on the value of f prime c, I think your value is 4,000 or 4,000 in PSI, which is equivalent to 4 KSI. So if f prime c is smaller than or equal 4,000, your beta equal 0.85. So this value equal 0.85 times c. I can figure out the value of c equal 8.8 inch. The nominal moment equal area steel time F yield time D minus A divide 2. Put your numbers. Area steel equal 5.08. F yield, and be careful. F yield is 60. It's okay. 60 is good. But it's keb per inch square. Keb, remember, it's in keb. Okay. Your depth is given 21.5. Guys, the difference between 24 and 21.5, 24 is the total depth or the overall depth or the overall thickness. But D, which is 21.5, is the distance between steel reinforcement and the top of this the cross section. So D is given 21.5 minus A, how much? 7.5 divide 2. I can figure out my value, 5.08 times 60 times 21.5 minus 7.5 divide 2. This value equal 5,410.2. What is the unit? Units are very important. What are the units? What is the unit for this moment? Remember, your stress was in keb per inch square and everything in inch. So your final one will be keb dot inch or keb time inch. I don't like inch in my moment, so I will divide this number by 12. Your final answer will be 450.85 keb foot. But I'm looking for what is the design moment. I'm not looking for what is the nominal moment. I'm looking for what is the design moment. So we need to multiply this value time phi. Do you agree? Do you agree? If we multiply mn time phi, the final answer can be called design moment. No, Kudi, not KSI. The stresses was KSI. So if you figure out the units, this one is inch square, this one keb per inch square, and this one in inch. So your final unit will be keb inch. I need to divide it by 12 to be keb foot. So my step right now, I need to figure out the value of phi. Few moments ago, I told you we have another table. We need to figure out which one I will use, this value or this value or something from this equation. based on what is the relationship between strain in steel and yielding and 0.005. Okay, what do you think about this triangle? Hey, remember this value equal 0.0003, and this value of depth, how much? 8.8. C, 8.8. We are looking for this value. So this value can be included in this little triangle. Can you make triangle similarity between this one and this one? Yeah, we can do. Let me do it here. We have this shape, epsilon t, 0.003. This distance is 8.8. So the remaining distance will be 21.45 minus 8.8. How can I get this one? Go back. The total distance between the top and the steel reinforcement, 21.5. The distance between the top and the neutral axis, 8.8. So the remaining distance will be 21.5 minus 8.8. 21.5 minus 8.8. This one will be 12.7. So your triangle similarity, you can do it like this. This value divide the corresponding one equal this value divide the corresponding value. The only unknown in this equation is strain in steel reinforcement. Okay, 0.003 times 12.7 divide 8.8. Your value equal 0.0043. By the way, epsilon yield equal E steel divide F yield. Value of E steel 29,000. 29,000 if you are talking about KSI. 29 million if you are talking about PSI. Divide F yield. Yielding is given in KSI. This is the reason why I use 29,000. So it's 60. So I can figure out the value of yielding. 29,000 divide 60. Your value, I'm sorry, I have a mistake here. I'm sorry, guys. I have a big mistake. It's F yield divide E steel. I'm sorry. So 60 divide 29,000. I'm so sorry. So 60 divide 29,000. Your value equal 0.002. So the value of strain in steel reinforcement equal 0.0043. The value of yielding equal 0.002. I believe epsilon in steel greater than epsilon yield and smaller than 0.005. Do you agree? Yeah, 0.004 is greater than 0.002 and smaller than 0.005. So I am in this situation. We are in this situation. Second case or second situation. So I need to figure out value of phi equal to this equation. So your value epsilon t 0.004, epsilon yield 0.002, 0.002. So I can figure out my values. So phi equal 0.65 plus 0.25. What do you have else? Epsilon t minus yield epsilon T, how much? 0.0043 minus yielding 0.002 divide 0.005 minus yielding, I think. Yes. So your final answer will be minus 0.02 divide 0.03 times 0.25 plus 0.65, 0.84. So your design moment equal 0.84, which is phi, time the design moment that you reach 450.85. 450.85. So your final answer will be 379.5 kb foot. So this called design moment. So just a very small part we covered today, because all of this stuff covered last week. How to figure out the value of CF of A, how can I figure out the nominal moment, capital MN. The new part today, we need to reach the design moment. So we need to multiply this nominal value by something called reduction factor, phi. So how can I figure out the value of phi? We need to figure out the value of strain in steel reinforcement. This value can be done or can be figured out using triangle similarity. Once you figure out the value of strain, you can figure out which equation I will use or which value I will use for phi. One more time, phi can be called strength reduction factor. It accounts for something we didn't consider in our design. Actually, factor of safety is used all the time to consider something we missed. Which something you missed? I don't know. Something is missed. Probably in the future, I don't know what will happen. Okay? So first case, we talked about everything is given. The cross section is given. The steel reinforcement is given. We need to figure out the design moment. On Friday, we will learn if we are looking for steel reinforcement. If I'm looking for area steel, how much? We will figure it out on Friday. But until this moment, do you have any question?